Hello and welcome. This is the summary of Chapter 12. So we talked a little bit about effective charge. One of the big things is this is our repeating trend as we go from left to right, say from lithium on across to helium. We then have a resetting when we get the sodium of the effective charge. We have a few ways of approximating the effective charge, whether we take S to be simply the number of core electrons or if we use some more sophisticated methods. But the key is that we get an increase in the effective charge from left to right with really no periodic inconsistency. And we get a slight increase as we go from top to bottom down a group of the periodic table. So we get an increase from left to right that gives us our different behavior of metallic elements on the left side, non-metals on the right side of the periodic table, and then we restart that trend with each new row of the periodic table. So what is the general size of an atom? Well, we can take the sort of idea that the radius of a particular atom compared to the bonding atomic radius. The bonding atomic radius is always going to be a little bit less than the sort of atomic radius would be if you had a separated atom. This particular figure is assuming we have some sort of single bond, maybe like between two chlorine atoms. So the bond distance between two chlorine atoms, if you take this bond length is going to be a little bit less than 2 times the pure atomic radius that the chlorine atom might have if it were a separated atom. So the atoms are getting a little bit closer together to each other than the radii would be if they were not forming this bond together. So the bonding atomic radii trends are actually what we see listed on the sort of next slide that we'll take a look at. We can use that chart to help predict bond lengths of molecules. We can also just use the ideas of relative atomic size from the chart that our atomic size is decreasing from left to right. So as we go left to right, our effective charge increases. That's going to help decrease the size of the atoms with the same trend. So as we go left to right, we get an increase in effective charge and we get a decrease in size. And then when we think about going from top to bottom, down a group of the periodic table as we go from top to bottom, despite our effective charge increasing a little bit, our size actually goes up because we have now a larger valence shell, bigger atom as a result. So this slide here is showing us the trend of size from top to bottom, increasing size. If you notice that is a trend that does not have any inconsistencies from top to bottom. And then also we have a decrease in size from top to bottom, at least with our main group elements. We don't see any variations here. Well, we see a little bit of variability within the transition metal series. That's really not anything to concern ourselves with at this point in terms of why we get a little bit of variability within the transition metal block. So we can see the size of elements is decreasing from left to right across the period due to effective increasing nuclear charge. And then from top to bottom, we get an increase in the size of the atoms due to the larger valence shells of those bigger atoms just simply being larger. We can then remind ourselves that if you compare, say, lithium to lithium plus, if you lose an electron, the atom becomes much smaller. Same thing, beryllium going to beryllium 2 plus smaller. So anytime you have the cation of an atom, the cation is always going to be a little bit smaller or even a lot smaller if you lose the entire valence shell. And then if you go to the opposite case where you start adding electrons, if you add electrons, that's going to add to the size because we're adding to the repulsive electron particles around the atom. So if you go from having 8 total electrons on oxygen to 10 total in the case of O2 minus, bigger ion in the case of O2 minus. So all of the anions are larger than their neutral counterparts. All of our cations are smaller than their neutral counterparts. And so one thing that's helpful to remind ourselves is that cations are smaller than their parent ions, anions are larger, but whenever you have 2 ions, say you're comparing the size of K plus and Cl minus, whenever you have a constant number of electrons between your 2 ions, then you're really looking to the proton count. We have 19 positive particles, but only 17 positive particles to hold in the same number of electrons. So K plus ends up being smaller than Cl minus, despite the fact that chlorine as an uncharged atom would be smaller than an uncharged atom of potassium, using our general left to right trends for atomic size whenever their charges are exactly the same as each other. So now, whenever we have an isoelectronic series, that's the series for which the electron counts are constant, we then look towards the number of protons to help us understand the size trends. More protons makes for a smaller atom, so Al3 plus is going to be smaller than magnesium ion, smaller than sodium ion, which is going to be smaller than fluoride, which is smaller than oxide ion. So our general trends in first ionization energy, then the energy it takes to remove an electron, as we get a general increase from left to right. We notice that it was increase, then a slight decrease, then an increase, then a slight decrease. So you see the slight decrease occurs in the NP1 group of elements, and the slight decrease here occurs with the NP4 group of elements. And this we can attribute due to the larger type P orbital being the electron being removed here. So we're taking an electron away from a higher energy subshell. And then in this case here, we're removing a spin paired electron, so it was slightly more repulsive and slightly easier to remove as a result of being a spin paired electron. So this is just removing a higher energy subshell, and then in the case of the MP4, then removing a spin paired electron, which has some repulsive energy that's destabilizes, if you will, that particular configuration. So it makes it a little bit easier to remove that electron. So I1 is generally the ionization energy. The first ionization energy is generally becoming a little bit smaller from top to bottom. So we go down a group, the ionization energy generally decreases. Now this is a general trend. Now we do see a few instances where the I1 actually increases from top to bottom in a few cases, and this can be because, or we can reason these out due to the increase in effective charge with the same trend. So if that increase sort of becomes a bigger factor than the increase in size from top to bottom, then the I1 actually can slightly go up from top to bottom. And it does in a few instances. So we have two counter-opposing trends. As we go from top to bottom, the size of the atoms are growing bigger, the valence shell is further from the nucleus, so it's generally easier to remove those electrons as a result, despite the fact that they do have a slightly higher effective charge. In a few cases, the effective charge is big enough apparently to make the ionization energy actually increase in a couple instances from top to bottom. The S and the P blocks show a larger range of values for S1. So when you're comparing the transition metal, the D block I1s, there's a little bit of a pattern here where it doesn't always fit the pattern of increasing from left to right. So it's a bit of a pattern, but it's a small change in the D block. The S and P block show a pretty big change in ionization energy from left to right. And so this is looking at some of those ionization energy trends. So again, seeing the general decrease as you go from top to bottom. You go down to the noble gas group, you get a decrease, halogen group a decrease. So you get a decrease, but you see a few instances where you get an increase. So I'm just circling a couple of these cases where we do get this increase in the I1 as we go from top to bottom. But for the most part, you get a decrease. So whenever you're comparing a trend, you're usually comparing from top to bottom that you get this expected decrease in ionization energy from top to bottom, but then you get the increase and then a slight drop, then increase, slight drop, increase, and that becomes periodic throughout the periodic table in terms of having that sort of pattern emerge. And you get a little bit of variability in the transition metal series that is not something to concern ourselves with in this chapter. So some of these irregularities, if you talk about the MP1 versus the MP4 being slightly higher or slightly lower in terms of ionization energy than we expect, you might just sort of do a quick comparison between, say, beryllium, and let's compare that with boron and carbon and nitrogen and oxygen and fluorine real quick. So with these particular elements, we go from being a 2s2 to a 2s2, 2p1, 2p2, 2p3, and a 2p4 configuration, 2p5, 4f. And so if we think of the relative energies of these orbitals, you can think, okay, beryllium's 2s up here in relative energy, 2 electrons. Now the energy it takes to remove and ionize that electron is just the difference between here and the energy of that orbital. This is corresponding to our ionization energy. And so then if we make a more stable 2s orbital, because we're now for boron has a higher effective charge, smaller atoms, so we are going to stabilize our 2s orbital. Same thing as we go to carbon, same thing as we go to nitrogen, same thing as we go to oxygen, same thing as we go to fluorine. The 2s electrons for these atoms are going to require an even greater amount of energy to remove them. In other words, their ionization energy for the 2s subshell is going to increase as we go from beryllium on across from left to right across the periodic table. So if we're comparing the ionization energy of the 2s electrons, we can see that we're just going to get this increase from left to right across the periodic table without any periodic inconsistency. The issue with boron is that the 2p subshell, which is higher in energy, requires then less energy to remove that particular electron, because the outermost valence electron is the 2p1 electron from boron, which now goes above the energy of the 2s subshell. Actually, I'm drawing this in the wrong spot. So let me draw boron's 2p here. So the issue with boron is that its 2p1 electron goes higher in energy than the 2s2 energy of beryllium. So if you compare the ionization energy of the 2p1 electron from boron, it's not very high. It's not as high as you would expect, or as it would be to remove a 2s2 electron from boron. So if you notice in the case of carbon, then for carbon, this becomes a little bit better in terms of the energy of the 2 electrons in those 2p2 electrons, smaller atom, closer to the nucleus, a little bit lower in energy. The same thing for nitrogen. So it becomes harder to remove the 2p1 electron. So the issue is to remove the 2p1 doesn't take as much energy for the case of boron. Then it goes up for carbon, goes back up for nitrogen. And then in oxygen, we're spin pairing an electron, which destabilizes that particular subshell. The other 2 electrons go back down as you would expect. Then we get 1 electron going down for fluorine, and now we have 2 spin paired electrons that are now higher, but relatively compared to oxygen, a little bit lower in energy. So this serves to then lower oxygens because of the spin repulsion. Fluorine still has spin repulsion, but it's better than oxygen, or they're more stabilized because smaller atom, closer to the nucleus. Neon, even better. So it takes even more energy to remove one of those electrons. So this leads to the zigzag behavior of our ionization energies from left to right. So our MP1, MP4, a little bit lower than we expect, but this is just because of some configuration configuration differences as we go from left to right, that we're not removing the same type of 2s electron. If we were looking at the energy it takes to remove the 2s electron, that's continuing to increase as we go from left to right without any periodic inconsistency. So it's just a little bit of a nuance to what ionization energy is really looking at from left to right, and why we get this break in periodic behavior, or this break in the general trend that ionization energy increases from left to right, though this particular break is completely periodic, that the MP1 and the MP4s are all always a little bit lower than we expect in terms of their ionization energies. So electron configurations, just to remind ourselves, we lose the energy from the highest, it's actually the largest orbital, I don't know if it's highest energy, it removes itself from the largest orbital, is the general idea of how we're losing electrons when we make cations. So the configuration of calcium 2+ is just the argon configuration. Iron 0 would be argon 4s2 3d6. So iron 2+ loses the larger 4s subshell first, it becomes a 3d6. Iron 3+ loses 1 more electron from the D, the next largest orbital, so it becomes a D5 or a 3d5. Anions just fill their electrons into the next higher energy shell. So neon is a configuration for oxygen, neon is a configuration for N3-, or you can say helium 2s2 2p6. We're just filling in 2 versus 3 more electrons for those atoms respectively. Argon- would be the configuration of argon, and then plus a 4s1, so just putting 1 more electron into that configuration. This equals the same configuration you'd expect for potassium. So this is not going to be a stable ion like O2 and O3- are, O2- and N3- are, because those are capping off their valence shells. If we want to put 1 more electron onto argon, not going to be something that's very easy to accomplish. So electron affinity is a measure of the energy associated with absorbing an electron into the shell of an atom. So an electron absorbed into the chlorine shell, making Cl-. The delta H of this reaction corresponds to the electron affinity of Cl. The one thing I like to point out is that the Cl- inverse of this reaction, making Cl plus an electron, is the ionization energy of Cl-. You can compare that or contrast that this is a different amount of energy than the energy it takes to go to chlorine plus an electron. This would be the I1 of Cl. And now you can compare the IE1 of Cl. So the IE1 of Cl, you can think here, this should be greater than the IE of Cl-. It's going to be easier to remove this extra electron from chloride than it would be to remove 1 more electron from chloride. The same reason why IE2, that's not an I, IE2, the second ionization energy of an element, so the IE2 of chloride, always going to be bigger than the first. So it's going to take more energy to remove that second electron, so it's going to take even less energy, though, to remove the extra anions electron to go back to neutral chlorine. So typically exothermic in terms of the electron affinities for most elements, though the noble gases are all positive. And then we have slightly higher, and usually sometimes not even negative in the case of the NS2 elements, and also in the NP3. These are slightly positive because we have to spin pair this added electron, so this is due to spin pairing. And then this is due to the higher energy, we're putting the electron in a higher energy subshell. by filling into a p subshell. So the ns2 group of elements and the np3 group of elements are all a little bit not as negative in the case of their electron affinities, and the most negative electron affinities are for the halogens. So these are our electron affinity trends, just kind of seeing this in table form. Most negative in the case of the halogens, really positive in the case of the noble gases, really positive or not as negative in the case of the NP3 group, and then same thing in the case of the NS2 group. But notice that most of the other elements in the periodic table have a negative first electron affinity, and this is due to the fact that these elements are, as we go from left to right, are more increasingly small, relatively high in terms of their effective charge, so it's generally beneficial or energetically favorable to have an electron absorbed into these atoms. So metals versus nonmetals, we see the metals form all positive charge states, so we make cations out of the metals, anions generally out of the nonmetals. Hydrogen's a little bit weird, and it makes a plus and a minus ion, minus with metals and plus with nonmetals. And so you can also see this chart here gives you some of the common charge states. Like we remember Hg forms Hg2, 2 plus versus Hg2 plus, gold plus 1 plus 3. So this chart's showing you some of the common charge states of some of the transition metals and some of the key transition metals. And so this is just showing us metals form positively charged states, nonmetals generally form the negative charge states, again, hydrogen being one out. So metals are generally regarded as being, most of the elements on the periodic table are metallic. They generally are thought of as having the shiny luster. They conduct heat and electricity well. You can pound them in the sheets, stretch them in the wires, so they're malleable and ductile. They're usually solids at room temperature, though mercury is an exception. Interestingly, cesium's almost a liquid at room temperature. Cesium's melting point is about 28 degrees C. So it almost, if room temperature was a little bit warmer, would actually go ahead and melt and would exist as a liquid. So the metals generally have low ionization energies. They form cations more easily. So since they have these low ionization energies, it's easier to remove electrons from the metallic elements. So metals, compounds can be formed between metals and nonmetals. They tend to be ionic. So of course, like NaCl plus minus are the types of compounds we tend to get between metals and nonmetals. Metal oxides tend to be basic and they react with acid. And so if we take like nickel oxide and add it to water, what it can do is release the oxide ions, so the O2 minus ions released in water. If the O2 minus ion is released, it can react with water to form two OH minus ions, as the O2 minus is actually a strong base. It actually will rip an H plus off of water, resulting in two OH minus ions. And if O2 minus forms in water, it's going to do this reaction to 100% yield. So we would define O2 minus to actually be a strong base if it were to form in water. And so some compounds don't particularly dissolve that well in water, so we can always add acid. That'll help us dissolve our compounds in water. So if we add acid, what we're effectively doing is taking something like NiO, nickel oxide, reacting with HNO3, and then just forming nickel nitrate, just the salt here, and then keeping the charge state constant for nickel, 2 plus 2 minus, and then forming water as a result. So we're going to need 2 of the HNO3s to give 2 H pluses off to react with the O2 minus to give us the 1 water. So we have some acid-base reactions that can go on between metallic oxides and acids. And so the key here is our metal oxides behave as bases. So we call this a basic oxide whenever we have a metal paired up with the oxide ion. That'll be a little bit different in the case of nonmetal oxides, but we'll talk about those in a minute. But nonmetals found on the right-hand side of the periodic table, they tend to be more wide in their types of states, so we can have solids, liquids, or gases in terms of the elements, in terms of how they exist. We can maybe even think of the halogen group F2 and Cl2 exist as gases at room temperature. Br2 exists as a liquid at room temperature. It's the only other element other than mercury that's a liquid at room temperature, I2 being a solid. Okay, and so we get, even within one group of elements, we get sort of a big difference between whether the elements exist as gases, liquids, or solids at room temperature. Solids tend to be more dull, more brittle. They're not really good conductors of electricity like metals are, so they're different in their behavior. they tend to have large negative electron affinities, so it's going to be easier for them to form anions as a result. So it's more energetically favorable for these elements to form anions. They also have high ionization energy, so it's going to be hard for them to form cations, so it's going to be more suited for these elements to form minus charged ions, and let the metals, which have the opposite case, low IEs, but not particularly negative or very negative electron affinities, so let them form cations. And then once you make something like Na plus Cl minus, you get that electrostatic attraction between the ions, and they're attracted to each other by electrostatic or Coulomb's attraction between oppositely charged particles. So nonmetals, substances containing only nonmetals or molecular compounds, so things like CO2, CH4. These are, and there's obviously a ton of examples of things that are molecular compounds, but these are always the combination of nonmetallic elements. Whenever we have the oxide of a nonmetal element, it tends to be acidic. So think about adding SO3 into water. We could form things like H2SO4, and then this is something that's an acid. So we could look at something like SO3 and term it to be a nonmetal acidic oxide. So these behave as acids, or they make acids in water. So metalloids have some characteristics of metals and nonmetals. They tend to be more electrically semi-conducting, so not really good conductors, but not also non-conductors, but somewhere in between. This makes these types of elements good for turning sort of circuits on and off somewhat easily. So these are good for computer chips. They also tend to have a wider variety of properties in terms of maybe looking more metallic, but then still being brittle, or not having the general abilities of being able to pound them into sheets and wires like you can metallic compounds. So usually high melting points, but then different sets of properties where they behave differently than metals. So kind of a blend between some of the properties of metallic versus non-metallic elements. So we got some different group trends. You might, some of these are pretty obvious. The alkali metals tend to form plus charged cations. The alkaline tend to form plus 2 charged cations. The oxygen group tend to form 2 minus anions. They tend to be non-metallic. Halogens form -1 anions, also non-metallic. Noble gases all exist as just uncharged atoms, so they exist just as atoms, which is really the only group of elements that do that on the periodic table. Most of the non-metals either exist as diatoms if they're a gas at room temperature, or some type of solid structure where the atoms are united together. And even if you think of iron, this is just kind of an aside for the moment, but there's some bonding here. Like if anything that's a solid has some type of bonding going on. In the case of iron, we would say it's metallic since it's a metal, metallic bonding. So there's some type of bonding between the atoms, or something's going on between the atoms in every single element, with the exception of the noble gases, which just exist as non-interacting particles in their samples. And so then hydrogen's a nonmetal. One of the things that you can see for hydrogen, there's a slide in this later, it has a very high ionization energy when you compare it with the other alkali metals. And so it behaves at room temperature and pressure as a nonmetal. It turns out, and there's some reports that have been done within the last couple of years, where if you really put a tremendous pressure on hydrogen, you can actually form what scientists believe is a metallic state of hydrogen. But it's when you put a really, really high pressure on hydrogen that's not attainable under standard conditions. So if you pressurize a hydrogen sample, it can behave as a metal, but the issue is that it's not going to do so. It's not going to exist as like hydrogen solid like sodium or lithium do under ordinary conditions. And so alkali metals are softer, though they are generally more metallic than, say, alkaline. Like our metallic character is increasing towards the alkali metals, even though maybe when you think of strong metals, you tend not to think of things like sodium and cesium. You tend to think more of some of your transition metals like iron and palladium and gold and those sort of metals. But some of their metallic trends are that they still have a luster, they still have some conductivity. Sodium is kind of weird, and you can actually kind of cut it with a knife, and it's a little bit softer. You probably have seen the examples where you throw it into water and it's very reactive, and potassium, kind of similar, very reactive. They actually kind of catch on fire. So very reactive in terms of their properties with water. Obviously, iron, gold, these metals are not as reactive with things like water. Alkali metals, let's look at some of these properties. One of the things I like to point out is how the melting points are actually dropping from top to bottom, which I don't know what you would have expected, but as you go to a larger element, cesium actually has a lower melting point. And this actually becomes a trend of metals in general, or things that have some inherent charge built up in them. We'll see this in the case of ionic compounds as well, that something that's really small like LiF ends up having a pretty high melting point. And if you have bigger ions like cesium bromide, the melting point here is a little bit lower due to the bigger ions. So whenever we have like ionic attraction or just electrons being distributed amongst many different nuclei, that the bigger the atoms, it's harder to accomplish that. The sort of the weaker those interactions, the lower the melting points. Okay, and so then it's kind of interesting the densities go opposite, but that's for some other reasons that we're not going to get into in this particular video. But the size of the atoms obviously increasing from top to bottom. The ionization energies are dropping from top to bottom, as we talked about earlier in the chapter as well. And so the issue going on with the melting points is worth contrasting with the halogen group, which we'll see later do the opposite trend. So alkali chemistry, so the famous reactions here, like you throw sodium or potassium into water, they kind of can ignite due to what ends up going on is that sodium is reacting with water to form sodium hydroxide, and then H2 is formed in the process. So we're going to need 2 sodiums, 2 waters, we make 2 NaOHs, and we make an H2 molecule, and that's a gas. This reaction is exothermic, it gives heat off, so the delta H here is less than 0. The heat given off warms the solution up and eventually can ignite the actual hydrogen gas. The hydrogen gas actually ignites in air to burn, and you see the flame being given off here when some of these transition metals react. And so you can sort of think here, the more reactive transition metals are actually the bigger ones. So you get a bigger flame or more reactive flame if you use a bigger atom. So cesium rubidium and potassium would give sort of more heat off because it takes less energy to remove one of these electrons from these atoms. So it's a little bit easier to remove the electron, faster reaction ensues, more energy given off, and then they can ignite more readily in water. So this chart here is now comparing the melting point trends of the alkaline metals. So they decrease as well as we go from top to bottom in terms of their melting points, just like the alkali metal group did. The ionization energies are dropping just as we expect. The size of these atoms are increasing. That's why the ionization energies are dropping. So the alkaline earth metals have higher densities and melting points than the alkali metals. So these are bigger atoms. And so they have higher melting points on average, and they also have higher densities. Their ionization energies are low, but not as low as the alkalis. The ionization energies of this group are generally higher if you go from left to right than the alkali metals, and they readily form, these elements readily form +2 cations, losing their 2 valence electrons. Now let's look at the group 6A, the oxygen group. Something interesting kind of happens here where the melting point actually goes up until we get to tellurium, then it starts to drop back down for polonium. The interesting thing for polonium is it's the only metal of the group. So the metallic trend is that metallic elements, when they're bigger, have lower melting points. And then for the non-metallic elements, as they become bigger, they actually increase in their melting points. And so that's just kind of an interesting counter balance here, is that our non-metallic elements, as they become bigger, they are going to increase in their melting points. This is going to be for something we describe later as polarizability, that the polarizability of non-metallic elements is going to be greater the larger they are, and hence the higher the melting points will be. But then for atoms that are going to share charge, it's going to be easier to share that charge when the atoms are smaller. And so then the smaller elements, in the case of metals, have higher melting points as opposed to the bigger elements, which have lower melting points in the metallic groups. So the ionization energy trend does exactly what we expect here, that we get a drop in ionization energy as we have an increase in the size of these particular elements. Let's talk allotropes for a minute. Oxygen can exist as oxygen gas, that's the more stable form. Ozone, higher energy. We can create ozone in the atmosphere by the reaction of sunlight with some of the different radicals that are present in the atmosphere. There's some discussions of this type of process in, I think it's chapter 18 in our textbook if you're interested. But ozone is one of the allotropes of oxygen. You get allotropes in the case of carbon as well, where the more stable allotrope is graphite. The more precious and expensive allotrope of carbon is diamond. where these are two different forms in the same element. Now let's look at the halogens. We get the same behavior of the halogens, though none of these elements are metallic, so we get an increase from top to bottom in the melting point. Iodine's melting point goes above room temperature, so this is why iodine is a solid at room temperature. Bromine has a boiling point above room temperature, melting point below, so it exists as a liquid. Gas in the case of fluorine and chlorine. If you weren't sure if a substance where it exists in terms of a solid, liquid, or gas at room temperature, just look up its melting point and its boiling point, and then compare with where room temperature is and what physical state it would exist at 25 degrees C. And so we get an increase in the atomic size of these atoms from top to bottom, and therefore a decrease in their ionization energies with the same trend. Halogens, all nonmetals, they have high electron affinity, so they tend to exist as anions in nature, -1 ions. They react directly with metals to form things like metal halides. So you can take something like aluminum plus Cl2 and form AlCl3 as a result. So maybe we'll take 2 aluminums, 3 AlCl3s, and make 2 AlCl3s as a result. So we tend to form these ionic compounds with the halogen elements. So noble gases, all non-metallic elements, no metals here, so we get an increase in our boiling points and our melting point trends for these elements. We get an increase in their size, we get a decrease in their ionization energies as a result. So noble gases have large ionization energies, large positive electron affinities, so they're not making cations or anions readily, and they're very unreactive as a result. So these exist in nature as monatomic gases. So these exist just as isolated atoms in their gaseous state, so helium, neon, argon, etc. These atoms just exist as isolated atoms within their samples. And so then hydrogen is kind of interesting in that it's a 1s1. It has the same one valence electron as the alkali metals, but itself does not behave as a metal, at least at room temperature and pressure. Though I was mentioning earlier, if you pressurize a sample, it seems like you can probably form a metallic state of hydrogen. It just needs this intense pressure in order to behave more as a metal. We don't tend to think of HCl as being ionic. This is still a molecular compound, so this has a very low boiling point, unlike NaCl, which has a very high boiling point. So we think of acid compounds like HCl as having H+, however they are really covalent in their nature. So HCl as a gas shares that electron pair, not existing as an H+ and a Cl- pair like NaCl does. When reacting with metals, hydride ion can form, so CaH2 would be calcium hydride for H- pairing up with calcium 2+. So hydride ion can form in the case of bonds of hydrogen with metallic elements. All right, so that's all for this summary video for Chapter 7. Thanks for the attention.